So let's actually try to use all of this framework and define essentially our system. So we're going to do 1, 2, 3. So we're going to look at basically our rubber network. I'm just going to define it as a cube, and we're pulling it in the one direction. So we're going to define, if I'm pulling in the one direction, what's going to happen? Well, alpha 1 will just be the new length in the one direction over our initial L naught, L naught, L naught, L naught. When I pull in the other directions, what's going to happen? So remember, I have my alpha 1 times alpha 2 times alpha 3 must be equal to 1. So I've already defined what alpha 1 is. So actually I could put it right here, L1, L naught. And I know that when I pull in the one direction, there's nothing kind of stopping the other 2 and 3 directions from compressing, right? Because when I pull here, the other material is going to kind of shrink in here. So they are going to, and we're going to assume this material is isotropic, behaves the same. So this will be the same. So basically, you can kind of treat this as like x squared equals 1. So you can, oops. So you can actually define it like that, or you could just keep it as alpha 1. So I could just do alpha 1 times x squared equals 1. So x is equal to 1, actually 1 over square root of alpha 1. So hence, alpha 2, alpha 3, and this condition is met. You can plug this back in essentially to, remember, we had our expression for delta S here, alpha 1, alpha 2, alpha 3. Plug that in, and you end up with this. Fantastic. Now, if I want to find what's the force in the one direction, I'm going to take the derivative of this function with respect to L1. I can do all that math, and actually, you know, we could actually do it in Mathematica, or you can do the math on your own. Oops. I'm going to stop this. Quit the kernel. Oof. For some reason, it doesn't like it. Come on. There we go. So for example here, I can do that my alpha, I'm going to say A1 is equal to L1 divided by L naught. A2 is equal to 1 to 1 divided by square root of A1. A3 equals A2. Del S is equal to minus K divided by 2. K divided by 2. K is a Boltzmann's constant, obviously. A1 squared plus A2 squared plus A3 squared minus 3. Take the derivative of del S with respect to L1. Li, excuse me. Li should be L1. I'm going to actually do that right now because I don't want Li. Boom, 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 boom. Boom. That's derivative. Multiply it by minus t times this, and we get our expression. So you can kind of see, actually, if I just do k times t times a1 minus 1 divided by a1 squared, and divide this whole thing by L naught, you're going to end up, let's go full simplify, backslash, full simplify, you're going to get basically the same answer there. Anyways, so we've got it. So we've got our system. We figure out the force in the one direction. So we can go a little bit further now. So I need to, basically, if I want to look at now the force, or the stress in the one direction, I have my force expression. A naught is just going to be simply, I'm pulling on this, basically the 2-3 plane right here. And it is going to be multiplied by this factor z. So the total number of subchains per volume. So that's going to be a key factor here. So I need the number of subchains z per volume. So multiply that out. When I look at basically n sub x is z, number of subchains per volume. So z divided by this is the volume. So I'll get out my number of crosslinks times kt times alpha 1 in here. So this is really important. So typically our restoring force is going to be written in terms of the molecular mass. That's something that's easier to kind of basically measure and study, and you'll see a lot of those values. So basically the molecular mass of the crosslinks is going to be the mass of the polymer divided by the volume, so density of the polymer over number of crosslinks divided by my Avogadro's number. So I'm just going to basically rearrange essentially that function here. So you see here we have the number of crosslinks, so I'm just going to rewrite it in terms of this. So we see here that our stress is going to be inversely proportional to this. Makes sense, right? Because if my molecular mass decreases, then what's happening? I have more crosslink sites. So makes sense to me. But we're not done yet. So I could rewrite alpha 1 in terms of stress. Actually, excuse me, alpha 1 in terms of strain right here. We could plug that back in to get an expression of stress versus strain. We are going to, again, we're looking at the limits of small strain, so we can negate this guy. So what we're left with is our Young's modulus is simply this. And this should make sense, just as we kind of saw right here. So this is our expression, a general expression for our Young's modulus for a rubber elastic system. The Young's modulus increases with temperature. That is an interesting finding. Why is that? Because my system is wiggly. If I have more energy in my system, it can wiggle more, and it wants to basically fight against that, or actually, it has a larger entropic restoring force. Similarly, again, molecular weight, we already kind of touched up on that. So this relationship that my Young's modulus increases is proportional to temperature is very uncommon. For other materials, as temperature increases, your Leonard-Jones potential, typically where it's stiff like this, it'll typically end up softening. So your potential changes and your Young's modulus changes as well. So that's a very, very cool derivation. Again, density, it breaks down, again, where our assumptions may be not valid. And it's very, very, very cool. So you can measure essentially that Young's modulus, and then in different regimes and Rouse and time scales. So there are some limits to this model. Again, there are cases where, again, strain-induced crystallization, so that happens quite a bit. If you pull long enough where your subchain basically is completely stretched out to reach the contour length, the contour length is just basically the length is going to be your number of monomers times the length of that subunit, then if you reach that length, then yeah, this assumption breaks down. Bond rotation can basically rotate around. Dangling ends, that also basically your Young's modulus may be lower because there's some dangling ends in your network. System drops below TG, in which case we go back to our old assumption. Too many crosslinks, again, not basically Gaussian anymore. Too few crosslinks, again, basically it's so long, it's basically, there's no real crosslink density here. So this is your rubber elasticity in a nutshell. So next time we're going to go into Poisson's ratio. There's going to be lots of problems with the rubber elasticity with more complex stress states, but you kind of just basically go through the same formalism and you'll be fine. All right, thanks. See you next time. Bye.